Hi there. This is going to be a series of tutorials where I teach some stuff about the Swift programming language with a focus on helping C++ developers learn Swift by showing some of the key differences between the two languages. If you know some C++ and want to get a jump start to learning Swift, or just want to learn some stuff about each language, then maybe this video will help you. I'm going to start with one of the biggest differences between the two languages, and that's the way Swift treats classes versus structs. So let's actually first start on the C++ side and understand in C++ what is the difference between a class and a struct. So here I have a simple project set up. We have a struct called thing. It has one instance variable that's an integer called x. And then in our main function, we go and we make an instance of thing and we assign its x to 5. And you'll see if I go and I build this, it'll print out some stuff and then it builds fine. Then if I go and change this to be a class instead of a struct, and I try to build it again, you will see a bunch of crap. And the important part here is this thing. Thing X cannot access private member declared class. What it's saying is X is a private member of the class thing, so we cannot directly access it from the main function. This highlights the key difference between a class and a struct in C++, and really the only difference, which is with classes, if you don't explicitly specify a visibility, then it defaults to private, whereas with struct, it defaults to public. In practice, just don't really use structs, just use class and specify your visibility explicitly. Either way, it's good practice to always specify your visibility explicitly. So you can see here, if I change it to explicitly say public, now we're back to whatever this is and it builds fine. So yeah, that's really the only key difference between a class and a struct in C++. They are more or less identical. Before jumping over to the Swift side of things, there is one more concept I want to cover while looking at C++, and that is value types versus reference types. I'm going to give some vague definitions, and then I'll hopefully explain them better with actual examples. So for a value type, it means that when you make a copy of the type, it results in two independent instances, meaning that if you mutate one, it doesn't actually mutate the other. Whereas with a reference type, when you make a copy of it, it results in two instances that actually refer to the same underlying data, and thus mutating one does mutate the other. In C++, we think of this more as pass by value or pass by reference because it's not actually tied to the type itself. So let's go into an example of this. Here, I've modified the main function to have my thing, and then it has my thing too, which is assigned to my thing. So we are making a copy of my thing. And then we say my thing.x equals 5, my thing2.x equals 3, and then we print them both out. And let's see what we get. We get 5, and we get 3. So that is showing that these are being passed or copied or whatever the term you want to use. It's behaving as a value type, where when we go here and say my thing2.x equals 3, that's not changing my thing.x. In C++, there's a very explicit syntax to get reference type behavior, and all we have to do is add an ampersand here. So what that's saying now is that my thing2 is not actually an instance of thing. It is a reference to an instance of thing, and it's referring to this exact instance, my thing. So maybe that was a little confusing, but effectively, my thing2 is just an alias now for my thing. And if I resave this and I rebuild and execute it, we can see now it's 3 for both of them. So what's happening here is my thing2 is now not an independent copy of instance thing. It is just a reference to the same underlying data as my thing. And thus, when we say my thing 2.x equals 3, we're actually overwriting what line 19 did to set it to 5. And so we get the same result. Or rather, we get both of them having the value 3 because they're both the same thing. So there's a brief rundown of passing by value, passing by reference, value type, reference type, whatever you want to call it in C++. Okay, now we are looking at Swift. Yay, I know everyone's excited. So what we have here is a similar set of code to what we had in the C++. We have a struct called thing with an instance variable called x that's an integer. We are then, for now, just making an instance of it and printing it. And I'm going to kind of walk through a similar example to what we just looked at with the C++ to highlight the differences between classes and structs in Swift. And I think it'll be clear how the conversation of value types versus reference types comes in. So first, if I run this application as is, just to get a baseline, we can see when we print mything.x, we get 0. Now let's add code similar to what we did in the C++. So we're going to say mything2 equals mything. So we're making a copy of mything, storing it in mything2. We're now going to say mything.x equals 5, mything2.x equals 3. We'll save it, we'll rebuild it and run it. And I forgot to print mything2. I will fix that. And now I'll save it and we'll rerun it. All right, just like before, 5 and 3. So what does this mean? If we think back to the definition of value types and reference types, this means that my thing here, and actually in general in Swift, thing is a value type. When I make a copy of it and put it in my thing too, these are now independent. So when I mutate one, it does not mutate the other. Therefore, at the end, they have separate values. Now, if you remember back to the C++, to get reference type behavior, we went before we declared mything2 and added an ampersand. If we do that in Swift, it completely fails to compile. I have it clearing, so you didn't see that, but if I get rid of that, you can see it yells at us. This doesn't mean anything in Swift. It just doesn't make any sense. This isn't Swift syntax. So if that's not Swift syntax, then how do we actually do this? The answer is that we need to change thing to be a reference type. In Swift, whether something is passed by value or by reference is not declared where you actually declare the instances. It is a property of the type. Structs are value types. Classes are reference types. So you'll see now when I change this to class and I rebuild and run it, now we're back to getting that reference type behavior from C++, where my thing and mything2 are both actually referring to the same underlying data. And so we start out by changing it for mything to 5, but then we overwrite it for mything2 to 3. And since they are both referring to the same underlying data, line 11 actually still mutates the original mything instance. So there's one more topic I want to cover in this video, and that is stack allocations versus heap allocations, which maybe surprisingly is actually related to this discussion of value types versus reference types in Swift. This may be slightly more advanced, but I'll keep it mostly simple. I'm going to assume that you already have a decent understanding of the stack versus the heap. If you don't, I'm sure there's plenty of good resources for it. But the only relevant details for this discussion is that the stack is really cheap to allocate new things onto, but its space is very limited and it can't change. It's fixed at compile time. Whereas the heap, it's more expensive to allocate things on the heap, but the size of the heap can change dynamically over the course of your program's execution. So as you allocate more and more memory from the heap, it'll actually grow dynamically and it'll grow as big as you need it to, assuming you reasonably stay within the bounds of RAM or swapping onto disk, or whatever. Point is, stack is heap to allocate on, but you can only do it in a very limited manner, and heap is more expensive, but anything that's big or can change size over time kind of needs to go there. So now you might ask, how does this apply to C++? In C++, whether something is allocated on the stack or the heap is not a property of the type itself. Thing could be a class, thing could be a struct, it doesn't matter. That doesn't impact whether it goes on the stack or the heap. In C++, you have to explicitly ask for heap allocations. So by default, when I just declare my variable like this, variable type space variable name, it is allocated on the stack. To ask explicitly for a heap allocation, you would write code that either uses the new keyword like this, and it returns you a pointer to a newly allocated instance of thing on the heap. I know that was a lot of words. Hopefully it made sense. Or in the more C style of things, if you're more of a C person, you might see it look something like this, where you say, this is going to be a bunch of crap. If this doesn't make sense to you, it doesn't matter. But this is the explicit system call to actually ask for space on the heap is called malloc. And what this line is doing is it is saying, I want to ask for space on the heap. I want it to be the size of an instance of thing. So however big an instance of thing is, that's how much space I want on the heap. And then this technically returns a void star, just a pointer to some piece of memory. And then I'm going to cast that memory as an instance of thing, assign it to this. This is a whole bunch of garbage that you probably don't care about. Don't do this. Just use the new keyword. Semantically kind of doing the same thing, but it's more clean. Actually, really, in practice, don't do either of these. Use smart pointers. Anyway, that's a topic for another day. But this does a heap allocation. And one thing to note about heap allocations is you have to explicitly get rid of them. When I just have thing, my thing too, I don't need to, I make this instance of thing, but I never need to explicitly get rid of it. It will implicitly be deleted when this function finishes running, or more directly, when this stack frame gets erased, if that makes sense to you. But for heap allocations, they'll live forever if you don't explicitly get rid of them. So you have to delete my thing to actually get rid of it. Or if you were using that malloc syntax, then you would call free on it. Don't mix those two, by the way. So that is how you get stack versus heap allocations in C++. Looking back at the Swift code, let's see how to determine when there's stack versus heap allocations here. In Swift, looking at the line where we say var my thing equals thing is actually not enough information to know whether it's going to be allocated on the stack or the heap. In Swift, it's actually a property of the type itself. If we have thing as a struct, it goes on the stack. If we have thing as a class, it goes on the heap. To prove that, we can do a small experiment where we profile how long it takes to make instances of thing when it's a class versus when it's a struct. So to do this experiment, we will make an instance of continuous clock, which is a type in the Swift standard library to help profile how long it takes to run some code. What we do is we say continuous clock.measure, and it'll measure the duration of whatever we put inside this closure. And so what we'll do is we'll do, let's say, 10 million iterations of just making instances of thing. And then we'll say, we'll assign the return value of the continuous clock.measure to this variable called duration. and we will print that out at the end. So let's start with thing being a class. So when it's a class, if we run this, you can see it takes about 0.72, 0.73 seconds. I'll run it a couple times just to show that it's somewhat moderately consistent. 0.73, 0.73. Okay, so around 0.373 seconds is about 730 milliseconds. Now let's change it to a struct. Now it took about 0.03 seconds. I'll redo it a couple times just to show again that it's reasonably consistent. So we got overall somewhere around 0.035 seconds, which is about 35 milliseconds. And then just to show another interesting detail, let's say we just take out the body of this loop altogether. So it's in debug mode, it'll still actually do the whole loop, it won't optimize it out. But if we run this now with nothing actually in there, we can see it still takes about the same amount of time. So if we do like no op, do nothing, it still takes about 35 milliseconds. And so the detail this is showing overall is allocating instances of structs which go on the stack is nearly free. It's about the same cost as just doing nothing each iteration, because practically speaking, allocating something on the stack is just moving the stack pointer. It's just a single add or subtract operation on the CPU. Whereas making instances of classes is actually a system called a malloc to go and get some space on the heap, and that is far more expensive. We can see in this case that's adding around 700 milliseconds total to this process. One more thing I forgot to cover is how we release heap allocations in Swift. So first, starting from the C++ side, like I mentioned earlier, whenever you explicitly allocate something on the heap, either using new or malloc, then you need to pair that with a corresponding delete or free in order to actually free the memory. And so to show this, what I've done is I added a destructor for the type thing that says thing destructor. And if I run this code as it is right now, ignoring the previous output, you can see it doesn't print that out. And that's because we never actually deleted this type. We're just leaking the memory currently. If I add a call to delete my thing, and then I rerun this, now you'll see it does say thing destructor because we are actually deleting the type. In modern C++, you'll actually rarely see people explicitly say new or delete or free or malloc or any of those things. Usually people these days tend to prefer smart pointers. So what I've done is I included memory, and I'll show just a brief example where the way people would write this currently is you might use a shared pointer. Let's make an instance called my thing, make shared thing. And what this line is doing behind the scenes is it is allocating a new instance of the thing type. That's what make shared of type thing means here. And the shared pointer is a wrapper around it that keeps track of how many outstanding references there are to this underlying heap allocation. And when there are none, it will automatically delete the heap allocation or free it. And so behind the scenes, this is essentially what we would call automatic reference counting, except usually automatic reference counting is that term is reserved for when the compiler does it automatically for you, whereas this is more runtime automatic reference counting, where every time when we make an instance of this type, the reference count is set to 1. If I then say auto my thing 2 equals my thing, now I'm making another shared pointer referring to the same underlying thing instance. So the reference count would now be 2. Then when the main function finishes, my thing 2 will go out of the stack frame and the reference count will be decremented. Then my thing will go out of scope, the reference count will be decremented again. It'll now be at 0 and it will automatically free the memory. So if I run this, we can see that's exactly what happened. We still get thing destructor printed, even though here we never have an explicit call that says free thing, but it just happens automatically. This is exactly what Swift has, but by default. Swift uses ARC, or automatic reference counting, which means at the time when you compile your code, the compiler behind the scenes goes and inserts retain and release instructions that will automatically do the same thing. So for example, if I say var my thing 2 here equals my thing, just like with the shared pointer example, it'll increase the reference count when I do this. And then when this program finishes running, my thing 2 goes out of scope, the reference count gets decremented. My thing goes out of scope, the reference count gets decremented again, it reaches 0, and the memory gets freed to show that I've added a D in it, which is the Swift equivalent of a destructor for the thing type. And if I run this, you can see that it does not print out what I want. Why is it not printing out what I want? Is it because I'm doing this in global scope? What if I do main and then I just do that in here? I assume now it'll work. Sorry, debugging in real time here. Okay, now it works. Well, there's an interesting quirk for you also. Apparently, when you just write everything in the global scope, then you're not guaranteed to get proper deinitialization, which I guess doesn't matter anyway. Okay. What I want to go over next are some practical examples where the differences between classes and structs will impact your code and how to best use them. So in this example, I declare an array of integers with 3 values where each of them are set to 10, print it out, then make a copy of that array. So I say var my values 2 equals my values. My values 2 is now a copy of my values. Then assign index 1, so the second value of my values 2, to be 20. So instead of 10, which it should start at. And then I reprint out both my values and also print out my values 2. And the question is, what do we expect my values to print out here on line 8? If we think back to reference types versus value types, if arrays are reference types, then my values should be actually mutated by line 7, because this would actually be a copy that points to the same underlying data, or rather refers to the same underlying data. Whereas if arrays are value types, then we'd expect that my values and my values 2 are completely independent instances that do not share the same underlying data, in which case my values should be unaffected by mutating my values 2. Well, if we build and run this, we see my value starts off as 10, 10, 10, which is what we expect. Then the second time it's printed, it is still 10, 10, 10. Whereas my values 2 is 10, 20, 10 because of the mutation we did on line 7. So what this tells us, and we can confirm it by actually going and looking at the documentation, is that array in Swift is a struct, which means it's a value type. And in fact, in Swift, I believe in the Swift standard library, at least as far as I'm aware, all collections are value types. They are all structs. So that's something to very much keep in mind as you're using. As a follow-up to what I just covered, if you're a very performance-focused software engineer, you may have the question of, isn't that really expensive and costly in terms of latency to have arrays be value types, where whenever you make a copy of it, it will implicitly go and copy all of the underlying bytes each time. So for example, you might think if you pass an array to a function, wouldn't it have to just copy all of the bytes? And the answer is that semantically and in all practical situations, arrays and all of the collection types in Swift, they behave as value types, but they implement a key optimization called copy on write, where the underlying bytes of the collection won't be duplicated or won't be copied until one of the instances is actually mutated. So let's look at practically what that means. I have the same code as before, where I declare an array called myValues, and then I say myValues2 equals myValues, so I make a copy of it. And what I've done is I added this function that what it does is it takes in an array and prints the starting address of the actual underlying bytes of that array. And based on what you might think, if it was actually copying all the bytes the moment you made a copy, so for example on line 12, when we say myValues2 equals myValues, if it was instantly copying all the data, we would expect that the two arrays would have different starting addresses. But in practice, if we run this, we can see if you look at all the letters and symbols and whatever here, these are actually the same exact memory address. And the reason is because we never actually mutated either of the instances after creating them. And since they weren't mutated, that means that copy on write was never triggered and it didn't have to copy any of the bytes. Whereas, for example, if I add in the line myValues2 at 1 equals 20 like before, now at this point where we actually mutate one of them, copy on write gets triggered and it says, okay, these two arrays, they need to behave like value types. So when one of them gets mutated, we do actually have to copy the bytes and give them separate storage. So if I rerun that, now you can see these two addresses are not the same because the underlying bytes were copied. I know this was a little bit advanced, but I think it's still an important thing to note to avoid some of the initial fear of, hey, isn't this a really big issue for writing performant code? Another note I want to throw in is actually an anti-pattern that you should really avoid, and that is making structs that behave like reference types. So in this example, we have a class called myClass. So myClass is a reference type because it's a class, and it has an integer inside of it. Then we have a struct that has an instance of myClass inside of it, and it offers two methods, getValue and addOne, where getValue takes that instance of myClass and just returns its x, its integer inside of it. Then addOne increments myClass.x. Then down here, we have some similar code to before, where we make an instance of myStruct, call addOne, so at this point the value should be 1. Then we make a copy of instance1, so we say instance1 copy equals instance1. Call addOne on the copy. Now, theoretically, as long as this behaves like a value type, which it should because it's a struct, then the copy should have value 2. The original should have value 1. And then we'll print them both out. You can see, unfortunately, we end up with both of them being 2, when really, if they properly followed value semantics, the original should have value 1. And the reason why this is happening is because myStruct, even though it's a struct, it's internally using a reference type, a class, as its underlying storage. And so when it says get myClass.x, it's the same myClass regardless of how many copies of myStruct has been made, because every time a new instance of myStruct is made, so for example on line 22, when we make a new instance and put it in instance1 copy, it's only making a copy of the underlying class, which is a reference type, meaning the underlying data does not actually get copied. Hopefully that made some sense. I know this is a little bit confusing, but the point is you need to be very careful when you make structs and then put classes or reference types inside of them. You can very quickly end up with really confusing bugs where you have structs that people think are value types, but actually behave like a reference type. The normal way you'd get around this is by implementing some sort of copy on write. Maybe I'll show how to do that in a follow-up, but for now, at least just know, be very careful when putting reference types or classes inside of your structs. To finish off this video, what I'd like to do is leave off with some general guidance on when to use structs and when to use classes. And the general guidance is as simple as you should prefer structs over classes, wherever possible, pretty much. Value types are far less error prone. In general, you're just going to have a much easier time writing bug-free code when you're using value types, whereas there's a lot more complicated ways that you can screw your code up when you start introducing reference types, which are classes. Also, structs being value types are just good for performance in Swift because they get allocated on the stack. In terms of when to use classes, look, there are going to be situations where you have to use classes, but what you should do is try using structs and then just keep using structs until you really run into some sort of situation where you need reference semantics. And that'll typically be in a case where, for one reason or another, it's just you really don't want to duplicate an underlying resource. Copy on write isn't an option for you, and there's just nothing you can do except make it a reference type and ensure that everyone who has a handle to it is using the same underlying resource. But I'd say those are actually few and far between. And if you look in the Swift standard library, and even a lot of other Swift packages, they have a lot of great inspiration, how even things that you would imagine being reference types, there are great ways to formulate them as value types that still are performant and also are much less error prone to work with. Thanks for watching. If you're a C++ developer and trying to learn Swift, I hope this was helpful to you, or I guess if you're anyone trying to learn Swift still, hopefully it was somewhat helpful for you. If there's other topics you'd like to see me cover, then maybe put them in a comment. Okay, have a good one.